my name is Mariano Zeron, and in this video, we're going to see how to estimate the error of a Chebyshev object. So the situation that we have is the following one. So let's say that we've already built a Chebyshev object for a given function, let's say a pricing function, that will be this one here, for which, as we already know, we need to specify a domain of approximation that we have here. We have to specify Chebyshev points, and we have to evaluate the function on the Chebyshev points, and that gives us a set V with these values over here. And we've come up with our Chebyshev object, Pn, which is the approximator to the function f. And that Chebyshev object can be expressed in terms of Chebyshev polynomials in this way, with these coefficients Ci, which are going to be very important for this particular video. And alternatively, they can also be expressed in terms of Lagrange polynomials, with these values Vi, which are the ones given by the set V. So the whole purpose is, or the aim is, to be able to estimate the error that Pn of x makes as an approximator to f. So of course, one way of doing that would be to come up with a very fine mesh or grid of points on the domain where we're carrying out the approximation, let's say points here. Very fine grid. And then what you do is evaluate f on those points and also evaluate the interpolator on those points. And then you can just compare the results. Take the maximum error, and that's going to be your estimate for the error in approximation. However, that has one big downside for us, which is that you need to evaluate f on many points. Remember that one of the things that we're always aiming to do is avoid having to evaluate the pricing function on any points. And for this particular approach, you would have to evaluate f on many points. So what can we do in order to avoid that? And what we're going to show is that using only the information that we have so far when we build the Chebyshev object, which is essentially this over here, using just that, we're going to be able to come up with a very accurate estimate of the error of approximation that Pn of x makes when it's approximating f. So our starting point is going to be the following result that we've already seen in other videos, but I want to write it down again, and I'm going to explain a few things regarding that theorem. The theorem says the following thing: if f is Lipschitz continuous, we have something called the Chebychev series. The Chebychev series, which is an infinite series, expressed in terms of Chebyshev polynomials, that converges to f of x. So what this means is that it converges pointwise. But the theorem not only says that, it also says that it converges uniformly, and it converges absolutely. And I'm going to say what that means in a second. But take a look first of all at the uniform convergence. So that basically means that the truncated Chebyshev series, which is defined by taking a look at this series and considering finite sums. So let's say this is f of n is just a function that we define as the sum of the first terms, or n plus 1 terms of this series. So it's going to be something of this sort. Basically means that f of n converges under the supremum norm, which is basically the one that takes the maximum difference between f of n and f on the domain of approximation. Says that this term tends to 0 as n tends to infinity. By the way, of course, we're only looking here at the very weak condition of being Lipschitz continuous. If we imposed a slightly stronger condition on f, which is that of being analytic, we would recover all the results that we've always been talking about, where we have that the approximation of f of n to f takes place with exponential rate. But for the time being, at least for the whole duration of this video, we're only interested in the consequence that we get by assuming that f is Lipschitz continuous. That's the only thing. So first of all, we got this expression here that we know is going to tend to 0 as n tends to infinity. And the second condition of this theorem is that it converges absolutely. And what that means is that this series, when we take the absolute values of these terms, that converges as well. It may converge to something different than f, but we know that it converges. And in particular, because of properties of Chebyshev polynomials in this particular case, one thing that we also can guarantee is that this series, the series of the absolute values of the AIs, that also converges. This is very important. And we'll see in a second how we can see that. So what does it mean for something of this sort to converge in general? So it means that when you give an epsilon value, let's say epsilon greater than 0, and you can think of epsilon as being the error of approximation in this particular context, we know that there is a natural number n, so that for all n greater than or equal to that capital N, we have that the tail of this series from the n plus 1 term, that is less than epsilon. This is what we have from convergence. This is just the definition. That is all. Now, one of the things that I want to do is link this value here, the tail of the AIs, to this error, which is basically the error that f of n makes as an approximant to f. So what do we have here? We have that from here, we have that f of n minus f. This is just by definition the tail of the Chebychev series. This is just taking f to be that series and f of n the first n terms, or first n plus 1 terms. Of course, the difference will only have the remaining part of the series, which we call the tail of the series. So it's this part here. Now, from here, one thing that we could do is take this inequality, which says that I'm going to be taking this thing here, right? This is just applying the triangular inequality. And then, knowing that the absolute value of the Chebyshev polynomials always goes between -1 and 1, we know that this is going to be equal, or it's going to be, sorry, less than or equal to the tail of the AIs, which we know is less than epsilon. So look at what we have over here in this corner. What we have is an upper bound for this error that we're interested in. And that upper bound is given by the tail of the AI coefficients, the absolute values of the AI coefficients, which we know has to be smaller than epsilon just by the definition of convergence. Now, so far, I've been talking about, from this theorem, I've been talking about this object here, f of n. But you might have noticed that we started talking about a different object, which is Pn of n, Pn, sorry, over here. Pn is the object that we can build easily. That is the Chebyshev object. F of n is a different object, but is very much related to Pn. And we've already spoken about the relationship between f of n and Pn in other videos. But the important thing to highlight here is that both of them, under this condition over here, converge to m essentially at the same time and at the same rate. So anything that you say for Pn in terms of it being an approximator, or the type of approximator that it is to f, you can also say about f of n, and vice versa. Anything that you say for f of n, you can say about Pn. So the reason why we deal with f of n here is just simply because the main theorem is stated in terms of f of n. But what I want to do here is first of all see how these coefficients a of I are a good bound for the error for this object, which essentially is going to be the same error that you would have with Pn as an approximator to f. Okay, so all is good so far. We've got this condition on AIs and how that imposes a condition on the error of Fn as an approximator to f. So let's assume that we suddenly had access to the AIs, the values of the AIs. So how would that look in terms of when we plot them in a graph? So let's say that you've got here epsilon. That's the value that you started off with, this one over here, that you can think of it as the error of approximation. And you start plotting these values AI, the absolute values of the AIs. So suddenly you would have these values here. The fact that we know that these AIs, the series, converges to 0, means that these values will have to go down at some point. So at some point, the f of n is going to start resolving the function. That is, it's going to start getting closer and closer to f. You're going to have these AI values converging to 0. But not only the AI values will go down to 0, but you have that the whole tail has to be less than 1, which means that at some point there's going to be a value n, this capital N value, which is stated here in the convergence condition, such that the whole tail over here has to add up to less than epsilon. So basically what we have here is that we know that there is this capital N such that the tail over here is going to be less than epsilon. Unfortunately, for most cases, finding this capital N is very, very difficult. If we had access to that capital N, given a particular pricing function, then we would know exactly the size of the Chebyshev object that we need to build so that we would have this epsilon value as the error of approximation. If we don't have n, we can do the following thing. Let's assume that we had a stream of AIs coming in, and you start plotting them. So we've got epsilon over here, and you start plotting the values of AIs as they come in. And we know that at some point, this will have to start decreasing. We don't have the whole collection of AIs, so we can't, from some point onwards, sum the whole collection of AIs. But what we can do is, given the first, let's say, k values of AIs, we can always take the last remaining 5, for example, and add them up, and use that as a proxy for what the tail should be. And that's what we do. So basically, as the AIs are coming in, we always take the last few of them and add them up. If the last few add up to something less than epsilon, what we know is that there's a chance that we could be in that kind of situation. That is, that we could be at this capital N for which we know this condition holds. So we know that it's not exactly the same thing. This is essentially the condition of having convergence. This is just a way of trying to find when this condition has been met. But one of the things we thought that we've seen every time that we apply this methodology to the pricing functions, which are the functions that we're interested in approximating, we've always been able to get good results. So in practice, this way of trying to identify when convergence has taken place has turned out to be an effective one. So we've seen the theory of how we can come up with an estimation of the error of a Chebyshev object. But now let's see how it actually performs on real functions. So I've prepared some code here. We've got a couple of functions that we're going to use to illustrate or to see how the error prediction performs compared to the actual error of the Chebyshev objects. The first function I'm going to use is the exponential of the sine function. And I'm going to be approximating this function between -4 and 4. So once we build a Chebyshev object for this particular function, what we can do is estimate the error that it makes as an approximant of the function in 2 ways. One of them is going to be the brute force way, which essentially what it does is consider 1,000 points, like you see here, 1,000 points in the domain, evaluate the function, evaluate the Chebyshev object, and compare the results. This is very accurate, but it's expensive because you have to call the function many, many times. The other one, as I presented to you before, only uses the values of the function on Chebyshev points and uses these values in order to come up with an estimate. And what we want to do is compare those 2 values for a collection of Chebyshev objects. So let's run the code, and I'll explain you what the results mean. So the first plot that you see here is the function. It just looks that way. And the second one, which is the one that we want to pay attention to, is the following. On the y-axis, we've got the error in log scale. The blue dots is the benchmark error of the object, which is calculated by evaluating the function 1,000 times. The x-axis shows the number of Chebyshev points used to build an object. So here, what we have is a collection of about 1, 2, 3, 4, 5, about 20, 25 different Chebyshev objects. So for example, here for 2021 points, we get an error of about 10 to the minus 4. The green dots represent the predicted error, which only use the values of the function on the Chebyshev points. And as you can see, before we reach machine precision down here, both of the errors are very close to one another, showing that the predicted error is a really good proxy for the actual error of the object. So this was the result for this particular function. Let me show you a function that you would use on a regular basis. Our old friend Black Scholes. I'm going to change the domain of approximation so that it makes sense for this particular function. It's going to go between 50 and 150 because the function has been chosen with 100 as its strike. And what we can see here is very similar behavior to the one that we saw before. So the brute force error, which is the benchmark, decays exponentially all the way down to machine error over here. But the green dots, which are the predicted error, go very close to the benchmark, again showing that they're a really good proxy for the error of a Chebyshev object. And in this way, what we can see is that you don't have to evaluate the function other than the times that you've evaluated in order to build the object. And so all is good if we had access to the AIs. Unfortunately, getting hold of the AIs can be complicated. The AIs are exactly the coefficients that define the Fn. As I mentioned at the beginning, Fn and Pn are essentially the same as approximators. The only difference is that f of n is difficult to have access to compute. Pn is very easy to compute. And that's the main difference between the two as approximators, at least for the applications that we're interested in. So we don't have access to the AIs, but we do have access to these Vs from construction. And the question is, how can we use them? So one of the things that we've already mentioned in another video is that if you start from the set V of values of f on Chebyshev points, which is enough to build your Chebyshev object Pn, one thing that you can do is apply the fast Fourier transform to obtain a set C. The set C is the set of these coefficients Ci, which allows you to express Pn in terms of Chebyshev polynomials. Notice that this expression is in terms of Chebyshev polynomials. Notice that the expression for f of n is in terms of Chebyshev polynomials. And the question is, are the AIs related to the CIs? And the answer is yes. So the way that these AI values and CI values are related is through a phenomenon called the phenomenon of aliasing. I'm not going to talk in a lot of detail about the phenomenon of aliasing. The only thing that I'll mention is one of the fundamental properties that it has, at least for our interests, which is that it allows you to express the coefficients Ci in terms of the coefficients AI. So in particular, for C0, you would have that's equal to A0 plus A to n plus A for n, and so it goes. And more generally, Ci is equal to AI, A to n minus I, n to n plus I, and so it goes. And the last one, Cn, is equal to A to n plus, A-n plus A 3n, A 5n, and so on. But notice one thing. If we had already reached this capital N, and that n is the one that determines how many of these coefficients we take, we know that these tails, that one here. So notice that C0 is going to be an infinite series of AI coefficients. Then you take that other tail here. And this other tail, all of them are going to be very small, which allows us to conclude that under the condition of convergence, we have C0 being very close to A0 and Ci being very close to AI. As I mentioned before, having access to the AIs can be complicated, but having access to the set V is straightforward, is what we start from in order to define Pn. But from V, applying the fast Fourier transform, we can get to C. So one of the things that we definitely have access to in a very efficient manner is this kind of plot, but with CI values instead of AI values. And what we do is once again, look for the condition that as the CI values are coming in, you look at the last few terms and you add them up and see what the value is. If the value is not below a certain threshold that you chose at the beginning, which is in a way your the error that you would like to have from the object that you build, then you can carry on sampling your function f at more Chebyshev points. If you've already reached it, you can stop. And applying this methodology to most of the pricing functions that we come across, in fact, to all the ones we've come across, we've always found out that the properties of these pricing functions are such that this methodology works in the sense that when this algorithm tells us to stop, you don't need to carry on evaluating f on any further Chebyshev points. We actually have the degree of accuracy that we wanted. So, of course, this can be used in order to know exactly when to stop the building process and knowing that you've got a certain degree of accuracy. Equally, if the object has already been built, you can also apply to the set V the fast Fourier transform, plot your values, or you don't even need to plot them, take your values, take the last few at the mark, and that will give you a proxy or an estimate of the error that you have with that particular object. So again, the main strength of this algorithm is that you avoid having to evaluate the original pricing function on a grid of points to then compare how your approximating object Pn does on those points to estimate the error. There is at least in practice, a very solid way, a very reliable way of coming up with an estimate of the error that your approximating object has. That's all regarding this methodology. Please get in touch with us if you've got any questions, and see you next time.